All right, let's go ahead and talk about the next part of these notes. So we did page 21 in class together. We're going to go and take a look at 22 to 25. Okay, so we're going to talk about limits at infinity. So the concept of limits as x approaches infinity means the following, right? What happens to y as x gets infinitely large? Right, we are interested in what is happening to the y value as the curve gets further and further to the right. Right, and then very similarly, we're talking about the limits as x approaches negative infinity. And so we're talking about what happens to the y value as the curve gets further and further to the left. Okay, and this is the new terminology that we want to go and refer to, is when x is approaching either positive infinity or negative infinity of our function. Right, so if I have positive infinity, this is my right. If I have negative infinity, this is my left. Okay, so examples 1 through 4, it says for each graph of f of x, we have to go ahead and find the given limit. Okay, so for example 1, right, if I'm looking at x is approaching negative infinity of my function, right, this means as my graph is approaching towards negative infinity, right, I'm looking to see where my function is going. My function is going up and up and up, so then my function, the limit is going to be positive infinity, right? As I am approaching x towards infinity, right, I'm going to keep looking up and up and up and up and up. So then it's also going to be approaching positive infinity from the right. Right, example 2, if I'm approaching negative infinity, I'm going to look at going up and up and up and up. So then I'm approaching positive infinity. If I'm looking towards x is approaching positive infinity, this guy is going to go down and down and down and down. So then the limit is going to be negative infinity. Right? In example 3, there's a couple things going on, right? If as x is approaching negative infinity, right, it looks like my graph is going this way. And we see that there's a dashed line. So here is actually a horizontal asymptote at y is equal to 4. And very similar with our rationals, right? As we are approaching those asymptotes, we got to make sure that it's getting super, super close. This one, the limit is approaching 4 as we're getting towards negative infinity. Right? And then this one does have a horizontal at y is equal to negative 2. So as x is approaching positive infinity, we're going to keep getting close and close and close to a negative 2. Right, go ahead and try example 4. All right, so that is looking at it graphically, right? There are ways that we can go ahead and look at it analytically, right? Whether it's direct substitution or using what we have used in the past, right? So we kind of talked about horizontal asymptotes. That is what we are going to go ahead and apply to today, okay? So there are 2 different methods. I'm going to go ahead and teach you guys both, and then you guys can just figure out which you would like to prefer for these problems. Okay, so the first one is we are going to go ahead and find the horizontal asymptote, right? So if my function right now, it says the limit as x is approaching infinity of 5 minus 2 all over x squared, right? So I'm going to first go ahead and find a common denominator. My common denominator is x squared, so I'm going to combine my 2 terms. So this becomes the limit as x is approaching infinity. That was weird. Infinity. So this becomes 5x squared minus 2 all over x squared. Right? Here I'm going to look at the degrees, right? The way that we would for our rationals. So this one has a degree 2. This also has a degree 2. So all I'm doing is just dividing the leading coefficients. In this case, my leading coefficient is 5 and 1. So then I have a horizontal asymptote at y is equal to 5. So the limit in this case, is 5. Okay, so that is one method, is using the horizontal asymptotes. Right, there is a second method, however. This second method, we like to go ahead and call plugging in infinity. Right, so if I were to go ahead and rewrite the whole entire problem, it's kind of like direct substitution, is I'm literally going to go ahead and plug in infinity So this then becomes 5 minus 2 all over infinity squared. And we all know that infinity is a very large quantity, right? So if I have a number divided by infinity, or infinity squared, or infinity to the 5th power, right? This number right here, this value, is going to be super, 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 super tiny. So this is a very small number, right? And so all I'm really evaluating is 5 minus that very small number, which gives me a value of 5. Okay, so really, like, that very, very small number is so, so tiny that it doesn't really matter. Okay, so there are the two methods: plugging in infinity and evaluating it using just like context clues about infinity, or you can go ahead and go back to rational equations and use what we know about horizontal asymptotes. Okay, so like for number example 6, I'm going to go and find the horizontal. So then this guy has degree 1, this guy has degree 1. So then my horizontal asymptote is at y is equal to 2 divided by 1, which gives me a value of 2. Boom. All right, my second method, I can go ahead and plug in infinity. So then I'm going to have the limit as x is approaching infinity, 2x minus 1, x plus 1. Again, I'm literally plugging in infinity, so I get 2 times infinity minus 1 all over infinity plus 1. Now, this is kind of an interesting concept, right? If I have infinity and I add 1 to it, it's still going to give me infinity, right? If I have infinity minus 1, it's still going to give me infinity, right? So these minus 1 and plus 1s actually do not matter. I can literally cross them out because, again, if I add something towards infinity, right, it's going to give me infinity. So all I'm evaluating now is just 2 times infinity all over infinity. And just like if we have 2x over x, right, my x's, or in this case my infinities, cancel out. So then I'm left with a value of 2. Okay, go ahead and try example number 7. Same exact thing. All right, I could trust you guys. You can go ahead and look at the answer key for these. Okay. All right. So we have seen this stuff before. So there are specific guidelines for finding limits at positive or negative infinity. This is positive or negative infinity of rational functions, right? In the past, right, we've seen if the degree of a numerator is smaller than the degree of the denominator, then the limit of the rational function is just going to be 0, right? If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is, this is when we go ahead and divide the leading coefficients, right? And then if the degree of the numerator is bigger than the degree of the denominator, then the limit of the rational function is either, in this case, positive or negative infinity. And we have seen this before. These are our quote-unquote oblique asymptotes. We've seen this before because this is basically the definition of a horizontal asymptote. Okay, last class we talked about the vertical. Today we're going to talk about the horizontal. Okay, and the way that we like to say it is the line y is equal to L is a horizontal asymptote of the graph of f of x if the limit of x is approaching negative infinity of f of x is equal to L, or the limit as x is approaching positive infinity of f of x is equal to L. Okay, again, L is just the y value, right? And that makes sense. L is just the limit, right? So let's go ahead and I'm going to do a couple examples with you guys, and then we'll finish with example 10, part A. All right, so